Question six. Let's suppose that there is no outliers and fit data. The model fit well to data, so things are fine. So let's suppose that even though we had a some outliers corresponding to the cook's distance in the demo data. So once we make sure the model fit well to data and no influential outliers in our data, we may be pretty confident for that the findings that we found, the findings are appropriate, at least for the sample that we use in the analysis. However, we usually want to conclude that this finding is not just only for the sample that we analyze. Rather, we'd like to conclude in a populations beyond my sample. Actually, to reach this goal, we should assume my data achieve um, generalizability. And then to achieve the generalizability, our data should meet a couple of assumptions. And then in the class, you talk about a couple of assumptions. Um, there's a couple of assumptions that we need to check, and there are four assumptions that we talked in the lecture with Dr. Lee. And first one is no multicollinearity. What does this mean is that if your variables have too high correlations among them, what would that means? That means the variable is actually the same variable. Like, for instance, if you check the correlation matrix among your variable, and then correlation, or for instance, correlation is or are larger than zero point 0.8, that's almost the same variable. Then it really does not, the variable that you input in the predictors really doesn't have distinct features or distinct role in predicting your outcome variable. That means the too high correlations among the variable cause multi-collinearity issues. So your actually findings, primary estimates should be biased. And another one is homoscedasticity. That's hard to pronounce, I know. Homoscedasticity. I'm sorry. Homoscedasticity. Um, what does this mean? Homo means same, and staticity means scatters. So it means your errors are scattered constantly. So if you look at the left side of this lab note, if the homoscedasticity is achieved, the variance of the errors or residuals are constantly distributed or scattered across the line. It doesn't matter whether the line is tilted or like horizontal. It really doesn't matter. What matters here is whether the variance is constant across x. So at least the variance over here is the same across axis. If you look at the left side of the graphs, um, the when x is small, the variance is small. When x is get larger, the variance get larger. What does this mean? What does this mean? The variance of residuals are not constant across x. It changes by x. Same as for the second one as well. In that case, we could say homoscedasticity is not achieved, so the assumption is violated for the generalizability. That means we actually cannot trust the regression coefficients that we got from this model. And then the last two are actually pretty similar concepts. So independent errors. The errors are if the errors are correlated in some pairs of cases, that means the errors are not independent. So, for instance, we fit the model, and then there's some residual. But for instance, boys, girls. For instance, like boy has very small variance in error, but girl has really large um, errors. What does this mean? So gender might have some role to make the amount of errors to residuals. So that means the error is not independent. There is still some systematic variance can be explained by some third variable. In that case, the errors are not independent anymore, and then this assumption is violated. So you cannot generalize your findings because of there will be some third variable that could explain your data more. So depending on those variables, your coefficients may be different. And then the last one is normally distributed error. Your error, the residual should be normally distributed. So let's assume that if there is no systematic variance in errors, that means there's all errors are just randomly distributed. Then if we distribute those errors, it should follow some normal distributions. I'm talking about the error. So then if all errors are normally distributed, then you could say there's no systematic variance in your errors. So your normal distributions of errors can be achieved. Then your assumption is met. So we're gonna check these two assumptions in this lab.